Hi, I'm Or Hirschhorn from Tel Aviv University. I will present today our new graph-based approach to category-agnostic pose estimation. A fundamental limitation of conventional pose estimation models is their inherent category specificity. These models are typically designed to work exclusively within a predefined object category, restricting their use to the domain they were trained on. For example, to train a human face pose estimation model, it is needed to collect a dataset of annotated face key points with different lighting and appearance. Or, if one desires a sofa key point detector, a dataset of sofas should be collected. This might be problematic in real-world situations involving novel objects with limited training data. To tackle this problem, category-agnostic pose estimation, or CAPE for short, was introduced. CAPE allows us to predict the position of key points for any type of object, using just a single model, even when the model has never seen this category during training. This approach is powerful because it allows us to define key points in a flexible way, depending on the specific object we are interested in. Moreover, CAPE significantly reduces the cost involved in data collection, model training, and fine-tuning for each new class of objects we encounter. CAPE methods work by matching support key points with their corresponding points in the query image in a latent space. However, previous CAPE methods have treated key points as isolated points, ignoring the natural geometric relations between them. These relations are important because they provide strong foundations for improving key point accuracy, especially when dealing with symmetrical objects or when parts of the objects are occluded. We enhance key point localization by representing the input key points as a graph, which allows us to better capture the relations between these key points. Our problem statement is as follows. Given an input source image with key point definition and skeletal relations, we locate these key points in a query image. The support image can be from a new category that the model has never seen during training. Our approach begins by using a pre-trained backbone to extract features from both the support key points and the query image. We then refine these features using a transformer encoder, which leverages self-attention to enhance the quality of the extracted information. Next, we use a similarity proposal generator to provide initial guesses for the coordinates of the key points. Finally, a transformer decoder is used to accurately predict the location of these key points. We implemented the structure prior into the transformer decoder. Specifically, our design is based on CAPEformer, changing the decoder to a graph-based module. The decoder has three main components: self-attention, cross-attention, and a feed-forward network. Self-attention allows for adaptive interactions among support key points. Cross-attention augments support key points representation by extracting localization information from the query features. Lastly, we replace the feed-forward network from a simple MLP to a GCN-based network to process the output key point features as a graph. These layers further concentrate the key point feature, facilitating the exchange of information between neighboring key points in the graph. We evaluate our method on the category-agnostic pose estimation benchmark MP100. This dataset contains over 20,000 images from over 100 categories, including animals, vehicles, furniture, and clothes. As some of the skeleton data was missing, we collected skeleton annotations from the original datasets and annotated several categories with missing skeletal definitions. As can be seen in the qualitative results, the structure information incorporated in our method serves as a strong prior for localizing key points, helping in breaking symmetry and creating structure consistency between the key points. The first row of the figure shows an example of symmetry that confuses prior methods, but not ours, while the third row shows the method's superiority in preserving structure consistency across key points. More examples can be seen in the paper. And in the quantitative results, our graph-based approach consistently improves performance over the enhanced baseline on the different dataset splits, on average by 1% under the one-shot setting, achieving a new state-of-the-art. To assess the robustness of our model, we evaluate our network using images from different domains. Our model, which was trained only on real images, demonstrates its adaptability and effectiveness across varying data sources, such as cartoons and imaginary animals, created using a text-to-image diffusion model. Furthermore, our model performs satisfactorily even when the support and query images are from different domains. To highlight the contribution of graph information in handling occlusion, we applied partial masking to the support or query image before running our model. It is important to note that the difference between the two compared models is only our suggested graph-based decoder. Notably, our model can predict key points even when a significant portion of the support image is masked. This suggests that the model has learned which key points are relevant and matches them based on structure. For instance, the model accurately predicts most of the key points of the sofa, while the baseline is confused by symmetry, breaking the structure of the sofa. To conclude, we introduce a novel approach for category-agnostic pose estimation by representing input key points as graphs. This method takes advantage of the important geometrical structure within objects. Additionally, we've provided an updated version of the MP100 dataset, now featuring skeleton annotation for all skeletons. Our code is publicly available. Thank you for listening.